So a little bit about our speaker, Anna Riddell. Anna's interest for science and the changing size and shape of the Earth piqued Anna's curiosity, leading her to undertake a bachelor's degree in surveying and spatial sciences at the University of Tasmania from 2007 to 2011. Upon completion of her degree, Anna joined Geoscience Australia as a graduate in 2012, where she worked in the Geodesy and Positioning Australia programs. Recently, Anna has submitted her PhD thesis on research about how the Australian continent is moving. Anna will today give us a presentation entitled, "What Goes Up Must Come Down. Why is Australia Sinking?" All the best, Anna. Over to you.
Thanks very much, Steve, and welcome to everybody tuning in today, and also those that might listen to the recording a bit later if you aren't able to make the live event. It is wonderful to be able to present today. So it seems as if Australia is sinking, and we don't really know why. Today I'm going to take you through a bit of my PhD research about understanding how the Australian continent is moving in the present day. So we're very much focusing on what's happening now, as opposed to what happened millions of years ago. So we'll start with a bit of background information that outlines the motivation behind why I wanted to look at this question, and then move into investigating why it looks like Australia is sinking. So if we think about the Earth as we live on it, it's an incredibly dynamic and complex place. There are many, many processes that are both geophysical and caused by humans that cause surface changes on the Earth. And so one example that I think outlines this the best is if you think of ice and snow accumulation in the Northern Hemisphere in the northern winter. That's quite heavy, and it attracts mass and attracts gravity and actually causes the Earth's surface to depress a little bit. And then as that snow melts and redistributes around the Earth during the summer, we actually see a bit of a rebound of the crust. And so that's one of the processes that we might talk about when we think about surface processes that change the surface of the Earth. There's also other processes, if we think about in terms of mass or weight that sits on the Earth's surface, whether that's the change of the oceans and the currents and the tides. We have loading associated with the atmosphere. Of course, we have huge tectonic plate shiftings, which can cause earthquakes, and not to mention some of the other human effects that can change how our Earth shape and size might differ. Now, if we're starting to think about impacts and indicators of a change on our planet, of course, global sea level change remains one of the most important indicators. Now, in Australia, our cultural, social and economic identities are very closely tied to our coastlines, with about 85% of the Australian population living within about 50 kilometres of the coast. And we have a lot of critical infrastructure that's also very close to the coastline. So for us in Australia, understanding the impacts of sea level change is quite important. A couple of examples. Here's a picture of the Gold Coast. I think this was in 2014, where they had, not only are we experiencing a change in sea level, but this was a large storm surge event. And so where you get a rising sea level coupled with an extreme event, you see some pretty interesting erosion patterns. And of course, that's getting pretty close to some of the infrastructure that's installed there in the Gold Coast. Another one from Woy Woy in New South Wales. I'm pretty sure this jetty was not built to be underwater. And so whether the jetty has sunk or whether it's a combination of a sinking jetty and rising sea levels, we start to see local impacts of how we might understand changes in our planet. And of course, let's not forget our Pacific Island nations, where global sea level rise remains just one of the absolute critical impacts to their infrastructure. This photo is on the Marshall Islands, and again, it's a high storm surge event or coupled with a high sea level, and you can see that's really close to their airport infrastructure. And so starting to understand the local implications and how we might start to mitigate or think about changing our lives around a changing planet. So we've talked a little bit about sea level rise and sea level change. But how do we understand that in a global context? So if you notice measuring sea level with a traditional technique like a tide gauge, the tide gauge is attached to land. And what happens if that land is moving is that you can influence your sea level change with vertical land motion. And to understand the absolute level of sea level change and tie that to other measurements of sea level from a satellite altimeter, say, you need to understand the vertical land motion component. And we do that quite easily by using GPS, or a global positioning system observation. If you haven't heard of GPS before, it's essentially a network of orbiting satellites that provide us with coordinate information or position information that we can determine down here on the surface of the Earth. And it's really useful for being able to measure changes on the surface of the Earth over time. So I use GPS to measure the crustal dynamics of Australia. And so we're very much looking at how Australia is moving. And we tend to use a 3D coordinate system to do that. So you might hear me talk about it in an X, Y, or Z coordinate system, which you think about as 3 axes. Or I might talk about in latitude and longitude and height, or northing, easting, and up. The 3 different components of how we can measure crustal dynamics. And we can add a 4th dimension to that when we look at change over time. And so here's a time series where we're considering data in the early 90s through to sort of mid 2000s. And you can see that there's a lot of squiggles. And that's what we're looking at, is how that change over time is happening, and if we can infer that as a process that's happening on the surface of the Earth. So using GPS to measure crustal dynamics gives us a really good indication of how the Earth is changing or deforming. And if we consider that in Australia, I want to touch briefly on a couple of concepts that you'll hear me mention today. One of those concepts is about noise. And so you might ask, well, what is noise? It's not necessarily what we're hearing with our ears, but it's when we talk about noise in a time series or a geodetic observation of surface change, we're very much talking about some of the random components of error that might be introduced into our measurements or our observations. And so white noise is very random or systematic, and you can kind of think about that as the grey and white screen that we used to get on our TVs when we lost lock to a channel. So that fuzzy, systematic, random sense of noise. We know that in a GPS time series, the noise or the error source is not always random. And so you'll hear me introduce the concept or the term about coloured noise, which is non-random. And so we consider those measurements to be correlated over time. And part of that is about how we break a GPS signal down into the components that we're interested in. So here we've got a plot. The top panel is looking at original GPS data. So that's data that's been collected every day over time from a period of sort of late or mid 2003 to 2018. And what we're interested in is breaking that signal down and understanding what's causing that change over time. And so you can do that by fitting a straight line, just to consider, well, if we were to look at the change over time and fit a straight line to it, what does that tell us about the change? In this case, we're fitting a linear trend. So we're fitting a straight line. Fine. Fitting a straight line like this assumes that the noise is white. We can also then look at some of the other squiggles involved in this time series. And so we're starting to look at, are there seasonal components? Do we see a change if this is up and down? Do we see a change in those time series with the seasons? This could be with water. In the wet season, you have more water. In the dry season, you have less water. And is there a surface change due to that? Once we remove the trend and some of these seasonal signals from a GPS time series, we're left with what we call the residuals. And this is what we're interested in to actually determine, is there something else in here that we could pull some useful information out of to understand that what else is going on around surface change? So an easy way to think about it is in the horizontal dimension. If we take the Indo-Australian plate and we fit its linear motion over time, so for the past 20 or so years, we know that the Australian plate has been moving at the rate of about 7 centimetres a year towards the northeast. but we're less clear on what it's doing vertically. Some previous research suggests that the Australian plate should be moving vertically between 0 and -1 millimetres per year, so we're getting that sinking feeling. But there are other models of long-term tectonic motion that suggest that Australia should be uplifting. So there's a bit of a conflict there between the current present-day observations and some of our really long-term tectonic models, and that's what we're going to dig deeper and dive into today. So if we think about Australia in terms of what might be causing some of these vertical motions or causing us to sink or to lift or to change, I want to touch briefly on earthquakes. So we know that we get a lot of large earthquakes around the plate boundary of Australia, but we also see a lot of chatter across continental Australia as well. And so this is just a plot illustrating that you can see all of the grey dots around the plate boundary, but you can see concentrations of grey dots in certain areas across Australia as well. And these are all of the earthquakes that were larger than a magnitude 3 in 1 year. So these are just over 2019. And you can see that we've got perhaps some distinct zones of seismic activity in the west, across the South Australia Victorian border, and also in Southeast Australia there as well. And so this is suggesting that we might see a bit of surface deformation from some of these earthquakes as well. Now you might be wondering at what scale I'm talking about making these measurements, and I'm going to argue that a millimetre matters. If we're starting to talk about processes of change that happen at the rate of a few millimetres per year, like sea level change or the change due to ice sheets and glaciers, and we're trying to look at natural hazards, which might be a couple of millimetres as well, whether that's the swell of a volcano or the rising of floods or predicting a landslide, we need to understand the uncertainty in our measurements at better than the measurement that we're trying to make. So in terms of measuring change at the rate of a few millimetres per year, we need to be sure that our measurements are accurate at a precision better than that. And particularly when we're starting to move into an age where we're starting to talk about driverless cars and automated equipment, we're wanting to chase maybe not millimetres in those cases, but we need to know that the foundation data that sits under that is accurate to a particular scale. So reference frame or datum matters. If you don't know where you are and what you're referenced to, how can you then make measurements in that system? So that leads us to my first research question, which was very much about understanding uncertainty. So we've made a measurement, but how good is that measurement? What is that level of certainty around that measurement is actually right? But we're going to go and look at that uncertainty in terms of the centre of mass of the Earth and how that relates to GPS positioning. So let me take you on a journey to the centre of the Earth. Now, unlike Jules Verne's fantastic book that was then made into a movie, there aren't going to be any dinosaurs or giant fungi here. We're going to make it slightly more technical, but I just liked the idea that we could go on a journey to the centre of the Earth. So we've talked about the centre of mass, but what is the centre of mass of an object? Well, let's consider an object that is uniform and has constant mass throughout, and it's like a cannonball. Now, the centre of mass is going to be coincident with the geometric centre of that object. So it sits in the centre or in the middle. But if we take a non-uniform object with unevenly distributed mass, like a pineapple, then the centre of mass is not going to sit in the geometric centre of that shape. It's going to sit towards the heavier end or the end with more mass. And that's similar for our definition of how we define the centre of mass of our Earth. So if we consider that mass is changing across the Earth's surface, here represented by an extraordinarily overweight cyclist, we see that the centre of mass also changes regarding how that mass is moving around the Earth's surface. And we can observe that location and the motion of the centre of mass using satellites. And we do that by understanding the motion or the geocentre motion. And so when we define the centre of mass of the Earth system as including its fluid envelope. So we're including all of the water bodies, including its oceans and tides, and as they shift, the center of mass is going to change relative to those. But if you take a network of observing sites that sit on the surface of the Earth, we consider that to be a geometric center in terms of the center of figure. And so this is the center that you might get if you were to calculate the center of Earth as observed by a network of sites on the Earth's surface, like GPS or a network of GPS sites. And we define the term as geocenter motion, which is the difference between the center of mass, including the fluid envelope, and the center of the figure. And that can change over time as the fluid envelope changes. Now we're able to observe this center of mass position and its change in time, or its motion, as observed by satellite laser ranging. But we can also model that and predict the motion with some of our models of how mass is transported around the Earth's surface. So just to touch briefly on what is satellite laser ranging, effectively you can think of them as giant space lasers. So there's a network of instrumentation all over the Earth. There aren't very many, maybe about 35, 40 sites where these space lasers sit, and effectively you're shooting a giant laser up to an orbiting satellite that's effectively a giant orbiting mirror in space, and you're getting a return signal reflected back from that satellite. And information about the travel time tells you how far away that satellite is, and if you measure to it many times, as much as you can see it orbiting around, you're able to calculate changes in what it's orbiting around, which happens to be the Earth's center of mass. And so by using giant space lasers, we can calculate where our center of mass of the Earth is. Now, we're lucky enough to have two of these instruments in Australia. We've got one here in Canberra up at Mount Stromlo, and we've also got one out in Western Australia out at Yarragadee. And these are very, very fantastic, high-performing sites, and I congratulate the crews that run those on such excellent results. So we've got our measurement of the center of mass. Now let's talk about how that relates to GPS. So the reliability of GPS is actually very focused on understanding where the center of mass is. So in order to make a measurement with GPS, you need to have a reference, or a 0 point, if you like, thinking in coordinate systems. And GPS positioning is in an Earth-centered, Earth-fixed system where that 0 point, or the origin, is defined by convention as being coincident with our Earth's center of mass. And so we've just learnt that that center of mass can move. So there's going to be a bit of uncertainty in the location of that, but there's also going to be a bit of uncertainty around the motion and understanding the motion of that 0 point, and that would directly relate and propagate back up into our coordinates as we receive them on the surface of the Earth. And of course, this has flow-on effects for any alignment of spatial data that we're trying to do. So you have your underpinning reference frame, or your datum, and then you're layering data on top of that. But if that datum reference point is uncertain, or there's a bit of fuzziness about where that datum sits, then any spatial data that you align on top of that is also going to have an uncertainty associated with that. And that's where we're starting to talk about in relation to our precise positioning, or our layering of spatial data. We need to understand that very fundamental base reference frame. So we do have an internationally defined reference frame, and that's called the International Terrestrial Reference Frame, where the most current definition is ITRF 2014. Don't worry about that too much for now, but just note that the origin is defined by satellite laser ranging and defined as the center of mass. When we think about GPS observations from a network of sites all across the world, that's actually coincident with a center of figure. And so we've got to align those two frames to make sure that we're measuring in the same system. Now, when the origin, or the 0 point of ITRF, is defined, it's assumed that its long-term motion over time is linear. So they fit a straight line through it and say that's how we define the long-term motion of our geocenter. And it's also defined with a white noise model. So remember how we talked about white noise being that assumption of random error. And it also means that you don't think that the measurements made over time are correlated at all. And we know that that's not really true. So my work looked at perhaps we could define a better way of understanding the noise or the error process in that reference frame identification point of the origin. So I took some of the SLR observations of the origin in 3 different coordinates. So we're looking again at the X, the Y, and the Z. And we can see that there's fairly clear evidence that there is structure, or if you were to fit a straight line, that doesn't fit the data particularly well. Even if we ignore the real scattered data prior to 1993, we can see pretty clearly that particularly in the TY component, there's kind of a banana-shaped bend. So fitting a straight line to that is not going to be the best representation of its change over time. Now, I call this an upside down banana. My husband argues, how can you have a banana that's upside down? Doesn't matter. Anyway, the fact is that there's a bend. It's a bendy banana shape as opposed to a straight flat line. And then again, if we looked at the Z component, I like to think that that's a bit of a Nike swish tick. There's a bit of a change that's clearly, again, not linear. And so making that assumption that the motion over time is straight just doesn't fit this data. So can we come up with a better definition or a better model to define the motion long-term over time of that origin 0,0 point? Now you might be thinking, okay, we've got this, you've said that it's squiggly, I get it, but why is it squiggly? Is it due to some geophysical process that's causing the center of mass to move differently over time? Or is it due to the observing technique? And it doesn't really matter which road we go down, it does represent an opportunity to improve future iterations of the ITRF. So let's look at some of the squiggles, what might be causing the changes or the non-linear bendy banana shape. The way that I did this was to not only look at the observations from SLR as we saw in the previous plot, but then to also look at some of the modelled or the predicted motion that we might expect if we model some of the contributions from steric sea level change. So that's the change to do with the salt and warming of the water and whether you see an expansion or a contraction in sea levels. And then I also looked at contributions from the different ice sheets to determining if they are also changing the geocenter. So we looked at Greenland, Antarctica, and some other glacial ice sheets. And we also looked at a big global hydrological model to understand if the changing of water that's not captured in the ice sheets, so tides, oceans, dam retention, could contribute to these squiggles or the motion in the geocenter. And effectively what we found was that the models are not very good at predicting that large variation that we observe with the satellite laser ranging. So here we've got 3 plots, 3 time series across 3 different coordinates. So we've got X, Y, Z, and this is a representation again of that origin point and its change over time. So it was the same as the red. So you can see in the Y, there's that bendy banana shape, in the blue squiggle line, and in the Z, there's that Nike swish tick. And the 2 predictive models of that geocenter motion are in the red and yellow. And so you can see that they don't match particularly well. But the fact that the 2 models, which were quite differently defined, that they match and appear quite similar, provides confidence that they're constructed fairly well. It's just that there's something else going on. And so that remains as a bit of a question for the geodetic community about what is going on in terms of our satellite laser ranging observations of that geocenter motion. If you are interested, this was the first research paper that came out of my PhD studies, so please go and have a look. I'd also be happy to answer any questions if you want to contact me a bit later to discuss that. But what does that mean for Australia? And what does that mean if we then, so we've talked about uncertainty in the geocenter in our reference frame, but let's bring that back up to the Earth's surface. And how do we apply that to our GPS positioning? Effectively, what we found was that by the assumption that we make by fitting a straight line, if you were to stick with that assumption, that introduces an extra 0.5 millimetre per year of uncertainty at a site, arbitrary site in Australia at Alice Springs, purely from that uncertainty in the geocenter motion. So that's the influence that uncertainty in the reference frame can then have and bring it back up to your GPS measurements. So now that we're back on the surface of the Earth, let's have a think about what the present day motion of the Australian continent might be. And this leads us into our second research question, which was looking at, is there a spatial pattern of vertical motion in Australia? Over what timescales do these occur? And can we pick out a dominant mechanism that's driving that vertical land motion or that sinking that we might be observing? And we're going to do that using the Australian GNSS network of stations. So here you can see a map, and that's all of the stations that we have in Australia that were installed as part of the AuScope program. And on the left is a picture of what a typical GNSS site looks like. So it's a concrete pillar with a fancy antenna for receiving the signal from the satellites, and off to the side there'll be a hut which hosts the electronics in it. So this is the network that I used for my processing, but I just want to briefly mention that with the Positioning Australia program, we're looking at upgrading and building new sites as part of our existing network. So here in the red sites, that's the map of sites that I used for my research. There's a plan to upgrade all of those. Then we're going to infill some of the gaps in that network. So you can see the purple diamonds, that's going to be building the new sites to form part of our Positioning Australia network. And part of the program is also signing agreements to bring extra data from some other third-party existing sites, which are all the green dots in Southeast Australia. And all of this data is openly available via the GA GNSS data portal. So if you're interested, I would encourage you to go and have a look there. It's a fantastic open data resource for geodetic and other research studies as well. So we've talked briefly about how we're going to measure it, but what are some of the other processes that might be causing vertical land motion in Australia? So we talked about a little bit about ice loading, but we've very much only talked about present day ice loading and the seasonal changes of ice loading. What about ice loading that occurred 20,000 years ago? So if you think of the last ice age, where there were large glacial ice caps in Northern America and Northern Europe, it's a lot of ice that's heavy and that's sitting on the crust, and it's going to depress that crust of the surface of the Earth a little bit. Come to the present day and the melting of these ice sheets, there's still tiny skerrigs of them left, but not very many. We're actually seeing still presently today a rebounding effect. As that heavy ice has melted, it's been taken off the crust, and we see a bit of a rebound effect. And we're still seeing that from ice loading that happened 20,000 years ago. And we call that glacial isostatic adjustment. Just think of it as ice loading happened a really long time ago, but we still see a bit of a rebound or a vertical movement because of that. Why do we need to consider that? Well, let's go back to our tide gauge scenario of measuring sea level. So here we've got a time series plot of tide gauge observations of mean sea level at 3 different sites in Northern Europe. And I just want you to focus on the bottom squiggly line here. So this is a site in Sweden. It's a tide gauge that's telling us that from that tide gauge measurement of sea level, that sea level at this point is falling at the rate of about 6 millimeters per year. You might think, hang on, that doesn't sound quite right. And you'd be correct. If we correct that tide gauge record for land motion associated with ice loading 20,000 years ago, so that GIA correction, we see that because of the vertical land motion, that changes the tide gauge record to become positive 0.7 millimeters per year in terms of what the tide gauge is now measuring if you correct it for that ice loading signal of vertical land motion. And then we take another correction or another adjustment for land motion as observed by GPS. So not all vertical land motion is caused by GIA. There might be other processes, local effects, earthquakes, whatever you can think of. We actually see that the tide gauge signal at that site is now rising at 2 millimeters per year, which is much closer to the global average. And so that makes a lot more sense, but it highlights the importance that we need to be able to use observations of vertical land motion at our tide gauge records to give us an understanding of what is actually going on with sea level change. Now, if we consider the comparison of comparing vertical land motion as observed by GPS and vertical land motion from a modelled GIA perspective, they are actually a bit hard to compare because they're in different reference frames. And so the next chunk of work was about aligning the models and the data so that we can compare them directly and look at signal of GIA in Australia. Now we expect that signal to be quite small. It might only be 0.2, couple of millimeters per year, and that it's a very small contribution to land motion in Australia, but it was worth considering and taking a look at anyway. And so the way that I did that was to reduce some of the squiggles in the GPS series. So we're talking about reducing the noise. Then I looked for a common pattern of motion. Can we find if Australia is moving consistently in the same direction across the whole continent? And then I compared that reduced data with a model of predicted motion from GIA. And what we found was that actually, yes, we do see a dominant pattern of motion across Australia. And so the take home from this is that it's not necessarily the direction of the arrows here, it's more that we're looking for a spatial pattern of movement. And yes, the pattern across Australia, if you look at what is the dominant motion, it's all in the same direction. And so Australia is moving the same way. It's not necessarily tilting or shifting, there is a consistent solid movement up or down. If we take that another step further, I was able to also pull out some other patterns that were associated with El Nino and also the Indian Ocean dipole. And so this is a tilting mechanism. So the first dominant mode of pattern of motion in Australia was straight up or down, but the next dominant mode of motion was a tilting. That's perhaps that we know is due to not only ENSO but other hydrological factors. In the wet season in the north, we see a tilt of Australia as it gets weighed down by the water, and then we see it tilt back a little bit. And then if we can compare these GPS estimates of land motion across Australia with the GIA variation, noting that GIA is going to be very small in Australia because we didn't have any of those large ice sheets, the question got a bit more complicated. So here in the plots, the colour and the motion in the dots, this is all vertical motion, that's from our GPS observations. And the background grid is the model of predicted motion that we were expecting from GIA. Not all of the GIA models are consistent. So that's okay, we expect that. There's going to be some differences because of the construction and the how they put those models together. But what I want you to notice is that the GPS estimate is pretty consistent of about a negative 1 millimetre per year, but the GIA models are pretty close to 0. But unfortunately, they're not given with an estimate of uncertainty. And so that means that we can't actually define whether these observations are these model predictions are any different from 0. Whereas it's quite clear that the GPS observations are significant, and we can tell that they are real. So the key points that I wanted to raise from this comparison of GPS observations of sinking and rising Australia and GIA predictions are that the GIA doesn't explain all of the vertical motion in Australia. And so what else could be causing vertical land motion in Australia? And that's the next question, really. Again, this was another piece of research that I published. If you are interested, please go and have a look. Otherwise, shoot me a question. I'd be happy to answer it. So let's think about what else could be causing vertical land motion across Australia as a whole continent. And could it be explained by earthquakes? Don't know, maybe. Let's find out. So Australia, we know, has, there are a lot of large, so I'm calling large as larger than a magnitude 7.5, earthquakes around the plate boundary of Australia. But as I showed in the introduction, there's quite a lot of small chit-chatter across Australia as well. And so we can use GPS observations to understand how earthquakes can cause crustal deformation or surface change across Australia, and not only in the horizontal dimension, but also in the vertical dimension as well. And so I just briefly want to touch on a couple of terms. You'll hear me use post-seismic and co-seismic. So it's really common to think about an earthquake and the instantaneous shift in land motion at the time of an earthquake, and we call that co-seismic, at the time of an earthquake. But what we also see is after that dramatic shift, we also see a bit of a relaxation that's much slower and it's not as big as the instantaneous shift, but it is a relaxation after the stress release from that earthquake, and we call that post-seismic. And so if we're looking at a GPS time series, we can see it really clearly. So these are looking at the north and east components of a site down in Tasmania after an earthquake down at Macquarie Island at the end of 2004. And the time series has been detrended prior to the earthquake. So you see it's nice and flat before the earthquake happened, and then there's a change in the earthquake after that happens. And so effectively that's telling us that the movement of that site changed direction. And then if we think about co-seismic, so this is the instantaneous shift. If you think about the east component, we saw it jump to the east, but it didn't change its long-term motion over time. So that was just an instantaneous shift. And if we combine these two observations of earthquake deformation or change after an earthquake occurs, we can start to understand how the Australian crust might be bending and buckling and breaking due to the stresses in the Earth's crust. So there was some really lovely research done a couple of years ago by colleagues at ANU, where they looked at the horizontal components of earthquake deformation around the globe. And as you can see, Australia is not immune to big earthquakes in our region. But here, the accumulation of deformation is actually quite small. So Australia, although we've had these big earthquakes, we're not in the zone where we see a lot of deformation in the horizontal component. But nobody's looked at the vertical component yet. And so that was why I wanted to go and understand if earthquakes could be causing some of the vertical motion in Australia. Now, the assumption has been that Australia, there was an assumption that Australia is a rigid plate. We're seismically inert. We don't see a lot of internal deformations. But the research from the colleagues at ANU was able to distinctly show that that doesn't hold true any longer. So simply by the change in the time series of GPS following the earthquake, if we were on a rigid plate, you would expect that the earthquake signal at the sites all over Australia would be the same. But what we see is that there's a spatial pattern that you can, the further away from the earthquake, the less the signal. So again, this is an earthquake down at Macquarie Island. So you'd expect a signal at Hobart to be a bit stronger than the signal at Melbourne, than the signal at Canberra, and this is what we see as well. And so in my research, I looked at just a snapshot of some of the big earthquakes around the plate boundary, and I wanted to understand if we could look at, if we could find those earthquake signals in our GPS time series. So we're looking at some earthquakes up in the Sumatra area. So the earthquakes here are represented by the green beach balls. So we're looking at the big Banda Aceh earthquake in 2004, there's one in 2005, one in 2007 and one in 2012, and then we jump down to the southeast and we're looking at the Macquarie Island earthquake in 2004, and also two earthquakes off the south of New Zealand in 1979, which is before our GPS period, and also one in a very similar location in 2009. And the blue squares here are the sites where I've been able to pull GPS data. Even though we have that really large network of sites all over Australia, unfortunately, a lot of those weren't installed until 2009. And so we've got a couple of earthquakes that happened before that, so we don't have any data for these earthquakes. The way that we're able to do that is we're able to compare the GPS observation of the earthquake, but we're also able to model the predicted deformation that we might expect from some of those earthquakes. And so to give you a really quick snapshot, this is using a very simple 1D layered Earth model where we're considering the different layers vertically profiling the Earth, and it's very simplistic. But we're able to predict the motion that we might then see from that earthquake and compare that to the observations from our GPS sites. So here we're looking at the earthquake down at Macquarie Island, and we're looking at sites at Mount Stromlo here in Canberra, Tidbinbilla, also fairly close to Canberra, and a site down at Hobart. And we're looking in the northern component, the eastern component's the horizontal, and here we're looking in the up component or the vertical component. The black dots and the blue squiggles are the GPS observations, but then the cyan, blue, and the cyan, magenta, and red lines are the predictions from a couple of different Earth models. What you can see is that we're most of the time able to fairly well predict the motion that we can see and observe in our GPS, but there are occasions where the models underpredict the motion that we're observing in the GPS. So this is suggesting that perhaps the 1D really simplistic layered Earth model is not really good enough. But the take-home story is that yes, we can definitely see deformation in the vertical component with these large plate boundary earthquakes, even though they're thousands of kilometres away. So if we take a look quickly at the Sumatran earthquakes, again, we can see that this is for 4 different earthquakes, 2004, 5, 7, and 12. Again, the time series is detrended prior to the first earthquake, and we can see a strong response in sites at Karratha and Yarragadee in Western Australia, but also sites in Darwin, which are over 4,000 kilometres away from where the epicentre of this earthquake occurred. And again, some of the earthquake models are fairly reasonably able to predict the observed motion. But again, we're a bit off on some of the other models. So again, suggesting that perhaps that 1D layered Earth model is not sufficient. So I guess the take-home story is that, yes, we can see post-seismic or deformation associated with earthquakes at our Australian sites, even though these earthquakes occur thousands of kilometres away from the Australian continent. And some of that post-seismic subsidence, we're mostly seeing a sinking signal causing these. It can reach up to 4 to 5 millimetres per year at specific sites. And this was most notable following some of the Sumatran earthquakes up to the northwest of Australia. I will note that, again, these were based on very simple predicted 1D layered Earth models, so there can be some improvements to be made there in the future. But another important point was when we define our reference frame and we use some of the GPS observations and GPS data to help do that, we only take a selection of events, of earthquake events, to include in that definition. And a lot of the offsets and the post-seismic deformation that I found in my new piece of research, they're not currently included. And so there's an opportunity there to help improve the reference frame again. So let's take a bit of a breath and bring this back out to the big picture. We've done a deep dive to the centre of the Earth. We brought that back up to the Australia, and we looked at how Australia was moving, and then we thought about, could earthquakes be causing some of that change? But what I want to highlight is that using our geodetic networks, we're able to observe and understand changes on the Earth, but how does that relate to the everyday Australian? You can't really feel the Earth move under your feet. But if you think again about understanding the measurements and the uncertainty and how we layer spatial data on top of that, that does have implications for some of the applications that we're starting to see that are wanting to use precise positioning, whether that be driverless tractors, increased positioning and integrity in aviation, in the construction industry. That layering of spatial data is all reliant on the foundation fundamental data set that sits underneath it, which is defined by our geodetic network of GPS and SLR and other geodetic observing systems. And so to wrap it up, in terms of vertical motion of the Australian plate, we see that the uncertainty in our origin or the reference frame will propagate into GPS coordinates. And we're using those GPS coordinates to make measurements and understand how Australia is changing. I was able to understand that Australia is sinking, but to tease out the reasons why it's sinking is getting pretty complicated. But we're also able to understand that these time series, as observed by GPS, can be influenced by some of the earthquakes that we see in our region. So I'm just going to leave you with this, this comment that in my world, everything moves. Nothing is stable. A millimetre does matter, and the models that we're using to understand how the Earth is changing can be improved. So thank you very much.
Excellent. That's great. Thank you very much, Anna. A virtual applause for an excellent presentation. I won't blow the microphone out with my gusty applause for such a great talk. We have had a few questions, and we've got a few minutes available. There's actually been a little bit of discussion on the chat line around. It was really initiated by Richard Blewett, and it'd be interesting just to get a comment from you, and that is reconciling some of these geodetic observations with long-term geological estimates that include not only subsidence but also uplift of key parts of Australia. How do you account for that?
Yeah, so as I said, these observations being geodetic in nature or observed by satellites, a lot of our observations only go back to the 80s. So in terms of geological timescales, we're talking about an absolute snippet of time. And I guess the way that we build in some of the long-term motions is that we do incorporate plate tectonic models into a lot of the processing. And so that goes into the really early analysis and processing of the GPS data. But my focus has been very much on understanding the present day motion, but it would be fascinating to link it back a bit longer. So when we talk about GIA, I mean, that's only going back 20,000 years, but could you go back further and explain some of the other geophysics and geological reasons? And so that'd be fascinating, but no, I didn't look at it.
Yeah, excellent. Yeah, it's a good call. And, there's an amazing record of, particularly from, the geological record of sea level change back through millions of years in Australia that would be interesting to look at how that trend matches with this.
Yeah, that's right. And it's sort of, you can tease it out a little bit further with tide gauge records of sea level, and then go back a little bit further with salt marsh and core records. But it's you've got to pick your focus. And so mine was very, very narrow in focus to keep it attainable, I guess.
Yeah, no, that's terrific, Anna. There were a couple more questions, but just in the interests of time and also because those earlier, they were questions that came through earlier and they were quite specific to particular slides and points. What we're going to do is we'll keep a record of those questions for Anna, for you to be able to respond to outside of this session, and we're quite happy to find a way to link that to the online presentation if people want to follow up on any of that. But I've got the names of the people that have asked those questions and the questions they've asked.
Yeah, that sounds great. I'd be more than happy to either contact them directly or provide written answers to those questions. That'd be really good.
Yeah, that's great. So Anna, I'd like to thank you again and personally congratulate you on an excellent presentation. I think it's pulled together a lot of work with some fantastically important implications, and I think it shows what a fantastic career of research and contribution to Australia's geoscience that you've been having so far. So well done. Thank you very much. And as a token of that, we give all of our distinguished Geoscience Australia lecturers a little memento as a thanks for that. And I'd just like to pass the inscribed laser pointer over to you to accept as a symbol of our gratitude and to mark the event. Here you go, Anna.
This way. Oh, look at that. Thank you very much.
Excellent. That was seamlessly done between Adelaide and Canberra. Beautiful work. Excellent. Thank you very much. I just to help wrap up here, I just want to say that please stay tuned to our Geoscience Australia seminar series. I think it's been a terrific success and a terrific way to keep getting our geoscience out to not only internally in GA, but out to our stakeholders and interested researchers. We currently don't have a confirmed speaker for next Wednesday, the 22nd of July, so please stay tuned for that. But I will also flag, though, that on Wednesday, the 29th of July, a somewhat related presentation will be delivered by Dr. Phil Cummins, and he'll be presenting on earthquakes and tsunamis caused by low-angle normal faulting in the Banda Sea of Indonesia. So please join us for Phil's talk, which will no doubt be engaging and entertaining. Thank you again, Anna. Thank you, everybody, for listening. Thanks for persisting through perhaps a slight technical challenge there. And don't forget, stay tuned. And if you wish, please follow up with these presentations that are now saved online. Thanks, everybody. See you later.